Okay, so now let's use the remaining of the time to start the LQ optimal design. In a nutshell, the LQ optimal design is a way to intelligently design the eigenvalues, to design the closed loop. Here, the eigenvalue placement, this narrows down to designing A minus BK for the feedback, and then A minus LC for the observer. You have to manually select the eigenvalues. The linear quadratic optimal control is designed based on the concept of you don't directly choose the gain, don't directly choose the eigenvalues, but instead you minimize, you have a target. We call this a cost function that you want to minimize. You want to minimize, let's think about, you want to minimize, let's say we're doing a case of stability control. We just want to regulate the system. This is our goal. We want to design the gain of feedback such that the system goes to the origin. Make x small in an efficient way. So I want to make x small. In other words, I want to make some quadratic form about x to be small. And then I want to do this without using too much control efforts. So I want to make the drop down, but in the meantime, not use too many control efforts. So this is penalizes large control efforts. In LQ optimal design, you don't choose the eigenvalues, but you choose Q and L. So in other words, you choose your objective, you choose your cost function in a way that reflects your design of keeping x small while not using a lot of control efforts. Let's say if your system is designed in a way that it's fine to have large control efforts. If the bandwidth of your system, the hardware is great, you can have large control efforts, then you can make R to be relatively small. Or you can make R to be relatively large so that large control efforts are penalized. And then Q and R, these are matrices. So treat them as, for Q, this is a n by n matrix to match the dimension of the state. That's Q. And then R is match the dimension of the input. If it's single input, then R is a scalar. If you have multiple inputs, this kind of design will make sure that all the control efforts are penalized in a way. So the dimension of R is the order of U times the order of U. If it's single input, single output, if it's single input, then it's a scalar. So that is the concept of linear quadratic optimal control. This seems non-trivial to solve at all for now. How, if the state is chosen this way, how can the overall, this is an infinite integral, how can I make sure I use just one state feedback design that will minimize everything along this infinite horizon? So that seems non-intuitive for now. But we know that, we know for sure, this kind of design, if the system is controllable, this kind of feedback gain, this feedback control design, will certainly be able, one of them will be able to do the job, because this kind of design can do, we know from our analysis, can do arbitrary closed loop eigenvalue placement. So we know this is for sure. We just don't know how to pick this one that will minimize this just yet. Now, let's take a look at the tools that we have so far. We don't know how to solve this yet, but remember when we did our Lyapunov analysis, this kind of infinite integration actually appeared already when we derived the Lyapunov equation more specifically. We used this kind of mathematical equivalence, right? We said the Lyapunov candidate V at infinity, which is half of x transpose infinity p times x transpose, minus its initial value, equals to the integral of V dot. And then V dot is this one, x transpose times q times x. So we did this, we know this actually works. The next major step is to somehow recognize that this actually can be put in a form that's close to this one here. I'll give you some hint. Here, if you plug in this one into that, you will get U transpose is X transpose K transpose. And then R, and then U is KX. The negative sign cancels with each other, so you have one negative sign, another negative sign becomes positive. So you have two actually quadratic terms about X. Okay? Here I had an index explicit. Here I didn't write the index explicit, but you should get the idea. These are both xt. So this is actually a big quadratic term about the state. If you treat this as your new Q matrix, then you have a connection to the Lyapunov analysis. The next step is to use this side of the tool a little bit more to fully write out, to fully analyze the cost function when the cost function is minimized. So we want to minimize J. Our goal is to minimize J. And the way we're going to do is to do some add and subtraction here. We know something like this works. So let's try. I'm going to add this one on the left-hand side. So this equals to V infinity minus V0. And then on the left-hand side, this is J, this big integration part, plus the integration part of this. So V is, this is our usual candidate of the Lyapunov function, that's V. So V dot becomes X dot, the usual computation, X dot Px plus X Px dot. That's the left-hand side, which is X dot is here. X dot equals Ax plus Bu or A minus Bk x. So that's our X dot. X dot is X transpose. And then inside is A minus Bk transpose times P times xt. So it's this times P, then times xt. So that's the first part. I left some space to write the second part. I have X transpose T, P times X dot T. So it's P times A minus Bk xt. So that is the left-hand side, using now substituting the system dynamics into it. This is about this is a quadratic in terms of x. Both of them are quadratic in terms of x. So we can combine all these together and then have this matrix. Adding into this matrix, we have a big quadratic function about xt. That's the left-hand side. The right-hand side, here, this is j, what we want to minimize, plus we at infinity, if the system is controlled to be stable, then at infinity, this is the usual result that this is going to go to 0. So we're left with minus half of x transpose 0 px0, which is one step away of obtaining the final result. On the right, we have this. We know this equals to the left. So we know j minus half of x transpose 0 px0 equals half of this big integration, a quadratic function of x. And then inside is a minus bk transpose p, pa minus bk, and then plus q plus k transpose rk. Okay. This is what we have mathematically. Can you guys take a look at this and tell me what is the minimum possible value for j? J is the cost we want to minimize. Now what we know is if you shift this term to the right hand side, j equals to this thing plus this thing. This is what's given to you, the initial value of the state. K is what we can design. What is the design of K that's going to make us to achieve the minimum of J? A of, say that again?
To make like what's inside plus, yeah, make the A minus BK term 0.
A minus BK term 0. Okay, we're on the right track. So classmate is saying that if I make this to be 0, then this becomes 0, this becomes 0. A lot of things become 0. But what about these? Just almost there. So the conclusion is that we should design K such that this entire thing inside becomes 0. Effectively, we make the entire thing on the right-hand side to be 0. Then the minimum possible value for J is this, depends only on the initial value of X. The details of how to make this 0 we'll talk about next time. But this part being 0 is exactly some important linear algebra. It's called Riccati equation or algebraic Riccati equation. Okay? That's, in a nutshell, the big pictures of optimal linear quadratic optimal control.